In this video, you're going to learn about hashing in JSON Web Tokens. Using these techniques, we'll be able to set up authentication for our application. Currently, all of the routes down below, getting to-dos, creating to-dos, getting an individual to-do, deleting to-dos, and updating to-dos, these are all public routes. Anybody can hit these and manipulate data that wasn't necessarily created by them. Once authentication is in place, all these are going to be private routes, meaning that you have to be logged in and you can only manipulate data that you actually own, which means I can't update a to-do that I didn't create. Now, in order to set all this up, we're going to have to come up with some way to authenticate these requests. What we're going to do is create a token system. This token, you can think of it like a string, is going to get sent back from our sign up and login requests. We don't have the login one in place just yet, but we'll get to it soon. The client is then going to take this token and use it to authenticate other requests. It'll simply pass it along as a header, for example, to a patch request, and it'll be able to make that call successfully after authenticating. Now, in this video, we're going to talk about hashing and authentication, how to actually create that token. To get started, over inside of the playground folder, let's make a file. I'm going to call the file hashing.js, and inside of hashing.js, we're going to get started by playing around with a very basic hash function. It's called SHA-256. Now, in order to play around with this hash function, we're going to need to install a module, crypto.js, that includes all sorts of encryption and hashing algorithms. Some you might have heard of, for example, AES, MD5, or the one we're going to be using, SHA-256. To install it, we'll run npm I, which is short for install. The module name is crypto-js, and we will be specifying the most recent version at 3.1.6 with the save flag. This is going to go ahead and install the crypto.js module. Once it's installed, we can move into our hashing file and import it. I'm going to grab a certain property off of the require return result. It's SHA-256, and the 256 comes from the number of bits that are the resulting hash. Next up, we'll set it equal to the return result from require, and we're going to require that crypto.js module, and now we have access to our hashing function. To hash a value, all we have to do is pass it into the SHA-256 function. I'm going to make a variable called message, and I'll set it equal to some string, something like I am user number 3. Then we can go ahead and actually hash it. I'm going to make a variable called hash to store the result. I'm going to call SHA-256, passing in the value message. Now, the result is actually an object. We're going to convert that to a string using toString, and then we can go ahead and print both values to the screen using console.log. Console.log, I'll use template strings for both. I'll print message colon followed by the actual message, the message variable, and I'll do the exact same thing for the hash. I'm going to call console.log with a template string, the hash colon space equals, then I'll inject the hash variable. With this in place, we can now run the hashing.js file and see what we get. Over inside of the terminal, I'm going to use clear to clear the terminal output. We are going to run node, and we're going to be running a file in the playground folder. The file itself is called hashing.js. When we run it, first up, we get our message, I am user number 3. Then we get this really long string that looks random, but I promise you it's not. This is the hashed result of the message above. Now, hashing is fantastic. Hashing is a one-way algorithm, meaning that given this message, I am always going to get this result, but I cannot get the original message back if I have the result. Now, I can prove that I'm always going to get the same result by simply rerunning the file a few times. I'm going to rerun it 4 times, and what do I get? I get the exact same hash value back because I passed in the exact same hash value. Now, hashing is used in a ton of different situations. For example, storing passwords in a database. It's a bad idea to store plain text passwords in a database, so what a lot of people do is they salt and hash their passwords. We'll talk about salting a little later, but you already know what hashing is. Hashing is a way to obfuscate the actual plain text password. When someone goes to log in later, they pass us the plain text password, we hash it, getting the result, and we compare that result to the result in the database. If the two hashes are identical, then the password is correct. If they're not identical, then the password must not have matched the one stored in the database. Now, we're going to be using hashing in a similar way to websites like SourceForge. SourceForge lets you verify that the file you downloaded is the one that you actually wanted because it hashes the file and it shows you that hash value. This means you can hash the file later. If you get the same result, you know it's the file SourceForge wanted you to get. If you get a different result, you know it's not the file that SourceForge wanted you to get, and you probably shouldn't use it because it could have viruses inside. This is the exact technique that we'll be using for our token. Now, this is not going to prevent someone in the middle from seeing the value. We're going to use HTTPS for that. We'll be securely transferring our tokens. This is, however, going to prevent someone on the client who gets the value from manipulating the ID and changing it to something else. Let's say I send back a token, and that token says this is for user number 3. The user then gets the token and they change it to the number 4, and they try to delete someone else's data. What we can do is use hashing to make sure that that value, the ID, doesn't actually get changed. If it does, we'll be able to spot that change and we'll be able to deny the user access because we know that they never actually got that token from us. They probably created the token on their own. Now, to illustrate how this is going to work, let's talk about the data that we want to send back from the server to the client. We're going to make an object and we're going to call that object data, and we'll set it equal to a regular object for now, specifying just one property, ID. The ID property is going to equal the user's ID inside of the user's collection. This is going to let us know which user should be able to make the request. For example, if I'm trying to delete a to-do with an ID of 3, but the user who created that doesn't match the ID of the token, then I know that they shouldn't be able to delete that because it's not their data. Right here, I'm going to set ID equal to the number 4. Excellent. This is the data we want to send back to the client. Now, the important piece of the puzzle is going to be making sure that the client doesn't set 4 to 5, send the token back to us, and say, hey, go ahead and delete all the to-dos for user number 5. That would be a really big security flaw. So instead, what we're going to do is we are going to create a separate variable, a variable called a token, and this is what we're going to send back to the user. The token variable is going to contain a data property that's set equal to the data object defined above. We can use ES6 to make that definition. Then we're going to go ahead and set a hash property. The hash property is going to be the hashed value of the data. If the data changes later on and we rehash it, we're not going to get the same value back, so we'll be able to tell that the data was manipulated by the client and we should not expect it to be valid. Right here, I'm going to set hash equal to the return result from SHA-256. We're going to pass in the string. Now, in this case, we have an object, so we can use JSON.stringify to convert our object to a string. I'll pass it in right here. Then we can go ahead and call the toString method, storing the resulting hash on the hash property. With this in place, we now have a token. Now, this token is not foolproof. For example, let's say the user changes the data ID property to 5. All they have to do is rehash that data, add it onto the hash property, send the token back, and they technically would trick us. What we're going to do to prevent this trickery is salt the hash. Salting a hash means you add something onto the hash that is unique, that changes the value. For example, if I hash the string password, I'm going to get the same result every time. But if I hash the string password with some sort of randomly generated value like this, I'm going to get a different result. And as long as I use a different salt every single time, I'm never going to get the same hash twice. And this is exactly what we want. We want to have a secret added onto the end, like a string. Some secret will do for now. And this is going to salt our hash. Now, the user, the client, they're not going to be able to manipulate this data anymore. They could change the ID from 4 to 5. They could try to rehash, but they're not going to have the secret, so their hash is going to be bad. When we then try to verify the hash later on, we're going to see that the data and the hash don't quite add up because the person who manipulated it didn't have the secret, and we'll be able to deny access for that request. Let's take a look at how we would validate that this token was not manipulated. Down below, I'm going to create a variable called result hash. This will store the hash of the data that comes back, the data that may or may not have been manipulated. I'm going to set it equal to SHA-256, passing in the actual data. This is accessible via JSON.stringify token.data. We're going to access the data property, we're going to hash it, and we're also going to use the exact same salt, some secret. Now we're going to go ahead and call toString on the result so we can get back our string value and we can make some comparisons. If the result hash equals, using triple equals, the token hash property, then we know that data was not manipulated, because if it was, the hash would not equal the hash provided because of the salt. This means that we can use console.log to print data was not changed. If the hashes do not equal each other, then we know the data was changed and we should not trust it because it's most likely not correct. Data was changed, don't trust. Awesome. Now that we have our two messages in place, we can go ahead and rerun this file from the terminal. And what do we get? We get data was not changed, and it wasn't. Right between here, where we could have changed the data, we never did. Now we can go ahead and actually change the data to make sure that the call fails. Down below, after the change, we should get data was changed, do not trust. So the man in the middle, they might try to do something like this. I might try to change the token data ID property to 5. Let's say I'm user 4. I'm really mad at user 5. I want to wipe all their data. I would change the ID, and then I would also create the hash. Token.hash is now going to equal the hash of the new data. SHA-256. We'll pass in JSON.stringify to convert our object into a string. We have that object. It's in token.data. Then we're going to go ahead and call toString. Now this is where the salt comes into play. The person in the middle, the person on the client trying to manipulate that data, they do not have access to the same salt. They don't know that secret because the secret is only on the server, which means when they try to rehash and update token.hash to a new value, it's not going to match the hash that we create later on, and we'll be able to tell that the data was changed. If I rerun the file this time around, we can see data was changed, do not trust. If I comment out these lines and rerun it, what do we get? Well, I never saved the file, so we get the same result. But if I save the file and rerun it, this time we see data was not changed, and that is fantastic. We now have a way to make sure that the data right here was never changed. In our case, this is going to be the token we pass back and forth. Now, this concept that we just went over, the idea of creating an object, hashing it, and verifying it later, this is not something new. There's actually a whole standard. It's called a JSON Web Token. And this is exactly what we're going to be implementing inside of our application. We could write all this code out and handle all the edge cases, but there's no reason to do that. There's a standard in place with libraries that make adding JWT, short for JSON Web Token support, really, really easy. I'm going to comment out all of the code we have so far, both examples, and we're going to go ahead and install this new library. We're not going to be using the crypto.js library inside of our actual application. This was for playground purposes only. The next library, a JSON Web Token, we are going to be using inside of our actual application code. Over in the terminal, we can use clear to clear the terminal output. I'm going to run npm I. The module name is JSON Web Token, and we're looking for the version at 7.1.9, which is the latest version, and I'll be using the save flag. Now we can go ahead and actually run the installer installing the module, and we can play around with it over inside of hashing.js. Essentially, what we get is two functions, one to create the token and one to verify it. Instead of adding all this code with the if-else statements, we just simply call these two utility functions. It's really painless. It's truly a fantastic library. Right here, I'm going to make a const at the top of the file, calling it JWT, and setting it equal to the return result from requiring JSON Web Token. Now, the two methods we're going to use are JWT.sign and, just below that, JWT.verify. JWT.sign, as you might expect, takes the object, in this case the data with the user ID, and it signs it. It creates that hash, and then it returns the token value. Now, JWT.verify does the opposite. It takes that token and the secret, and it makes sure the data was not manipulated. Let's go ahead and call it right now. I'm going to recreate our data variable of our data, setting it equal to the object with the ID, and I'll set the ID to the number 10 for the moment. Perfect. Now we can go ahead and call sign. The sign method takes the object. In our case, we have that as the data variable, and it takes your secret. I'm going to make our secret 123 ABC. Now the call to sign, it is going to return our token. We're going to want to store that in a variable called token. I'm going to comment out the other line, and this is the value we're going to send back to the user when they either sign up or log in. It's also the value we're going to store inside of that tokens array. Access will equal the string auth, and the token will equal the token we just generated. Now that we've signed our data, we can go ahead and print it to the screen and take a look at what we get. Console.log token. I'm going to head into the terminal and use clear. Then I'll rerun the file through Node. It's in the playground folder and it's called hashing.js. What do we get? We get another long cryptographic looking string. And that's exactly what it is. This string stores all of the information we need to verify that the data right here, was never manipulated. Now, if you want to take a look at exactly what makes up a JWT, you can take the value. I'm going to copy it from the terminal. You can go to your browser and head over to JWT.io. JWT.io has a bunch of documentation and explanations about how JSON Web Tokens work, but on the homepage, they also have a really cool tool. Over on the left, we can paste in our token. I'm going to delete the existing value and paste the value in, and on the right, we can see information about that token. There's three main parts to a JWT. We're only going to be editing the payload. We have the header, which stores things like the algorithm that was used. In this case, HS256 is used, and we have the type. It's a JSON Web Token. In the payload, we have the thing we set. We set the ID to 10, and we have the issued at timestamp, which tells us when the token was created. This is really useful data. Down below, we have the verification. This is where the actual algorithm is executed. This is where the hash is stored. Now you'll notice right now I have an invalid signature down below. That's because the secret right here is different from the secret I used to create the hash. Over inside of Atom, I used 123ABC. If I change this text box to 123ABC, now I have this signature as verified. This is what makes up a token. Everything before the first dot is the header. In between that second and third dots, that's the payload, that's our information. And the last part is the hash, which allows us to verify that the payload was never changed. Now that we have our token, we can go ahead and learn how to verify that it was not altered. JWT.verify is the function that's going to let us get that done. We're going to call it, passing in the token we want to verify, and we're going to be passing in the exact same secret. It has to be the same, otherwise it will not be validated. And what do we get? We're going to get the decoded result. I'm going to create a variable called decoded and print it to the screen. Console.log. The first argument will be the string decoded, so it's easier to find in the terminal, and the second one will be the actual decoded variable. With this in place, over inside of the terminal, I can now rerun the file, and right here we get our token, which we got earlier, and we get our data. We have our decoded data where the ID is 10. Now, if anything about the secret or the token changes before we call verify, the call is not going to pass. We're going to get an error. For example, let's manipulate the data by concatenating on the number 1. Then we can rerun the file, and what do we get? We get an error. It's an invalid signature. The data inside of the token is not what we expected. It's been changed, and you should not trust it. If the secret is incorrect, I'm going to add another C onto the end, and you rerun the file. What do we get? We get the exact same error. JWT is letting you know that something's not right with the data. Only when the token is unaltered and the secret is the same as the one used to create the token are we going to get the data back. And this is exactly what we want. Once we decode the data after the person makes the request with the token, we can use that ID to start actually doing the thing the user wants to do, whether it's creating a to-do, updating one, deleting one, or any other data manipulation. I know that was a long video, so thanks for bearing with me, but it's really important that you understand hashing and the JWT concept. Now that we have both of these down, we can actually implement them into our application, which is going to let us authenticate requests, which is the real purpose of this section. Thanks again for bearing with me. Hopefully you enjoyed it. Stay tuned. I will see you next time.